Welcome everyone to our first lecture on the deployment series. So to begin, to actually deploy something, we need to actually create a model. So let's head over to first a Jupyter notebook, and then we'll create a model there. Let's get started. Okay, here I am at a fresh notebook. I essentially want to start the process of deployment from the very beginning. So the first thing we need is a data set, and I'm going to run import numpy as np and import pandas as pd to get started. And to use a data set that we're all familiar with, what I'm going to do is read in the iris data set. So recall that the iris data set is one of these kind of world famous data sets that everybody always starts off with in machine learning. And it has a variety of features about flowers and then the class they belong to. So this is a supervised learning problem where we have these four measurements or these four features and then a species of flower. And so what I want to do is, let's imagine in the future, I have a researcher out in the field who picks a new flower and then takes the sepal length and width and then the petal length and width measurements. Eventually what I want them to be able to do is to log into a website, enter those measurements, and have a deep learning model produce a species prediction result. So that's kind of our final goal here. But in order to do all this, we need to start with historical data. So what's always important when you're deploying a model is think about your data set as well as what the final product should look like or what question you're trying to answer. In our case, we're trying to create a model that will, given four features of a flower, predict what actual species of iris flower it is. So first we need to do is separate this out into features versus target. So that means my X should be iris, and we need to drop that species column, and we need to drop a column, so we say axis is equal to 1. And now X is just all those features. And then what I need to do here is, similarly for Y, I just need to do the opposite, which is just grab the species column. Okay, so I have my X and Y, and as I mentioned before, typically X is capitalized because it's a two-dimensional matrix, and Y is lowercase because it's just a 1D vector. What I want to do is I want to now make sure, in order to do multi-class classification, if we take a look at Y, the unique values here are 3 classes, which means in order to actually perform multi-class classification with the way we're going to design our model, essentially 1 neuron per class output, what I want to do is somehow either one-hot encode this or use some sort of dummy variable to convert my actual Y values. One way I can do this quite easily is with scikit-learn. So there's lots of different ways you can do this, but scikit-learn does have one way. We can say from sklearn.preprocessing import label binarizer, run that import, and then say encoder is equal to an instance of this label binarizer. And essentially what we can do is say Y is equal to encoder.fit transform on Y. And then if I take a look at what Y looks like now, it's essentially one-hot encoded. So I have Setosa, and then Virginica, and then Versicolor here. All right. And later on, we'll talk about how you would actually know the orders there. It's just the same orders as they're shown in YUnique, Setosa, Versicolor, and Virginica. And there's a kind of a more official way to do that, which is actually off the encoder itself. So we'll show you how to do that later on, but right now, we've essentially one-hot encoded Y as needed. Now, it's time to do a train test split as well as scale our data. Hopefully this all seems very familiar. So we'll say from sklearn.model selection, import train test split. And we'll also say from sklearn. Make sure we spell that right, from sklearn.preprocessing, import min max scalar. Go ahead and run that. And now we say train test split. And I like to do this little shift tab trick to make sure I don't have to type out too much. Scroll all the way down until you see that example here, and let's go ahead and grab this guy. Okay, so we have our X-train, X-test, Y-train, and Y-test. Next thing I need to do, let me zoom out so we can see the whole thing here. We just say X and Y. Let's go ahead and choose the test size of 20%, so 0.2. And then to make sure you get the exact same random split I do, go ahead and say random state is equal to 101. You run that, and now you've created our train test split. Next step is to do scaling. So we'll say scalar is equal to an instance of this min-max scalar. We take our scalar and we fit it only on the training set. We don't want to assume prior knowledge of our test set. Run that. And now let's create our scaled xtrain, which is scalar dot transform on xtrain. And now let's create a scaled version of our xtest. So that's scalar dot transform on xtest. And you only need to scale your feature data. Whoops, make sure we say no dot there. Run that. Okay, so we have our scaled features, and recall we only fit to the training set. So later on what we have to do is we're going to have to actually save this scalar object in order to use it for new incoming data. So keep that in mind. After this, next step is to actually create the model. We'll say from TensorFlow, .keras.models, import sequential, and then from TensorFlow.keras.layers, import dense. Let's go ahead and create a very simple model. We'll say model is equal to sequential, and let's add a dense layer of 4 units with an activation function of rectified linear unit. And here the input shape, it's just 4 features, and we're actually not going to worry about batches or anything. So we'll just say input shape is 4 comma. We don't need to worry about the other dimension since we're not dealing with any 2D images, and we're also not feeding in things with batches. So finally after this, we'll say model add. Let's go ahead and add a dense layer here, and this will be our last layer, which means the number of units should match the number of classes we have. Recall we have 3 classes, Setosa, Virginica, and Versicolor. So units is equal to 3, and then the activation function here, because it's a multi-class classification algorithm, we need this to be softmax. Okay, and then finally we will compile this model, and we can do this with the atom optimizer. Again, you have flexibility over what optimizer you want to choose, but what loss you should be choosing is categorical cross entropy. And let's go ahead and also keep track of the accuracy in our metrics. So instead of just loss, we'll say accuracy. Okay, and make sure this is just compile without an S. Let's make sure we didn't commit any typos there. Run that, and you should have a model created for you. After this, it's time to train the model. So nothing new so far. We'll say from TensorFlow.keras.callbacks. We'll go ahead and import early stopping. That way we don't need to worry about choosing the right number of epochs. Let's go ahead and say early stop is equal to early stopping. And we're actually just going to use most of these defaults, like what we're going to monitor, minimum delta, etc. Last thing I want to do is I'll have patience be a little larger than 0. Since this is a very simple problem, we'll just go ahead and say patience is equal to 10. That way we can really see that curve flatten out for a bit. And now it's time to fit our model. We'll say model fit. We need to pass in x, which in this case is our scaled x train, and its corresponding y is y train. Then we'll go ahead and choose just a very large number of epochs since we have that early stopping mechanism to stop in case there's overfitting. We'll say epochs equal to 300, and then let's say our validation data is equal to scaled x test and y test. And then finally, we'll go ahead and set our callbacks. So callbacks is equal to early stop that we created earlier. We'll go ahead and run this. And now we can see it's training. Training shouldn't take that long, especially with the early stop. Let's go ahead and scroll down here. You may notice that it actually may take close to all the 300 epochs if it's getting better and better performance. You should get pretty high accuracy here. So let's go ahead and then see how it performed on our actual data. Let's grab first those metrics. We'll say metrics is equal to pd.dataframe, and we can say model history.history. Run that. Take a look at your metrics here. We can see loss, accuracy, val loss, and val accuracy. Let's go ahead and plot first loss against validation loss. Run that plot. Okay, so we can see here that both loss and validation loss were continuing to go down. In fact, we could have trained for even further. You can see that it was still headed down And let's go ahead and check out our accuracy metrics. So we take metrics and compare accuracy versus validation accuracy. Go ahead and plot these out, run that, and it looks like in the beginning we were overfitting a little bit, suddenly got a lower performance on accuracy, but eventually the model learns what to do, and it looks like it flatlined for quite a bit from epochs like 100 to 200, but eventually started to learn a couple of those kind of edge cases till it was getting around 80% accuracy. So if you're running the model just like we did, you should have achieved somewhere between 70 to 80% accuracy. And don't worry if your validation accuracy is a little lower than ours. We're getting a pretty good fit on this model. Okay, so last thing you can also do is say model.evaluate just to get that raw metrics data. And we can pass in our scaled x test, y test, and then say verbose is equal to 0. And then it will give you back the final loss as well as the final accuracy. So in our case, we're getting 80% accuracy on a test set of this model. This is the point in time where you would have to decide if those performance metrics are good enough for you. If we decide that our model is ready for deployment, if we decide that 80% accuracy is doable, then let's go ahead and ready our model for deployment. So how do we ready our model for deployment? Well, when I deploy my model, I want to make sure that I use all available data. So for the purposes of training and evaluation, I do my train test split. When it comes to the real world, for that researcher out in the field who's going to pick that new flower, I want to make sure that I'm providing the best model possible by using all the data. So what I'm going to do is the following. We'll say epochs is equal to length of metric. So we'll go ahead and just run the same number of epochs. Recall that was 300. And then I'm going to say scaled x is equal to scalar. And if I wanted to, I could then do a fit transform now on all my data, x. So notice I'm no longer doing a train test split. I've decided already that this performance is good enough for me, 80% accuracy. So that was on the test set. That test set, recall, is data that the model was not trained on. It's just evaluating it as it goes along. Now to provide the best model possible, I'm retraining on all my data. So it's kind of like a phase 2. And so far in all our lectures, we've kind of just been stopping on this evaluation phase. When it comes to deployment, we want to retrain on everything. So that's why I'm doing a fit and a transform on all my x data for my scaled x. So go ahead and run that. And now let's go ahead and create a new model. We'll say sequential. In fact, I'm just going to essentially copy and paste what we did before. So scroll up here. You can go ahead and copy and paste what is already there for us. Scroll down. And now we have our model. Go ahead and redefine your model. And then we're going to fit our model to our scaled x data, our y data, and epochs is equal to the previous number of epochs we chose, which was 300. Go ahead and fit that model. Okay, so once that model is done fitting for those 300 epochs, we're now ready to figure out how to save the model. So I'm going to scroll down here. We can see, if we kind of scroll towards the very bottom, how well the model is performing. So it looks like it's getting 96% accuracy. However, keep in mind, that's the accuracy on all the data that it's being trained on. So it's not a true fair comparison to say your model is now 96% accurate. It's 96% accurate when it gets to see all the data, train on the data, and evaluate itself on all that data. The true accuracy measurement that you should be using is this 80% accuracy, which is a much fairer evaluation of this model. So keep that in mind. So we'll come down here. And then what we're going to do is there's two things we need to save. We need to save our model. Luckily, we already know how to do that. So go ahead and say model save. And I'm going to save this as final iris model.h5. Keep in mind, this is already the same file name that we saved for you, but it's okay if you want to rewrite it. And then the next thing you need to do is save the scalar itself. New incoming data will have to be scaled in the same way that the model expects it. To do this, go ahead and import job lib or job library. This is actually built into Python, so you don't need to download anything to run that. And then say joblib.dump. And then the way this works is you pass in essentially the object that you want to persist as an arbitrary Python object, and then the file name, essentially the file path that it's going to go into. So I want to save my scalar object, and I will save this as iris_scalar, and the extension it should be scaled with is pkl, which stands for pickle file. Go ahead and run that, and it'll basically report back the string name of where it was saved. Okay, so I saved this .h5 file for my model, and if you end up using scaling for your model, you need to save that scalar as well. Now, let's see what this would look like if I want to predict on a new single flower. So we'll say from TensorFlow.keras.models, go ahead and import load model. This is essentially just to check that everything is working. And then I'm going to create two new objects. One is my flower model, a new variable, which loads up the final iris model. And I'm also going to say flower scalar, and I'm going to say joblib.load, and I'm going to load up the iris scalar object as well. And now what I should be able to do is, based off this model, predict something. So what we're going to see in essentially part 2 of this continuation is how to use this new loaded model and this new loaded scalar object and create a function that takes in this model, takes in the scalar, and takes in an example JSON, which is what our API is going to be working with when we actually deploy our model, and return back a prediction for the actual classes. All right, so I'll see you in the continuation of our deployment lecture series coming up next.